So we move to lecture 3 of periodically driven quantum systems. So as a brief recap, what did we do yesterday? So this was what we were doing. We said that this was our setup, right? It's a periodically driven Hamiltonian, and we wanted to solve the Schrödinger equation. And the claim was, that's what we tried to prove yesterday, was that this psi of t can be written as sum over n Cn e to the power minus I En times t phi n of t, where phi n t plus t, this is a periodic function, which is equal to phi n of t. Okay? And the other thing that we said was that these eigenenergies, right, which are now time independent, these are obtained from the stroboscopic evolution of the Hamiltonian, right? So these are the eigenenergies that correspond to UF, which is the stroboscopic evolution operator, right? So, and what we did was, we tried to get we tried to find ways to obtain the Floquet Hamiltonian. So basically what we were doing yesterday was to write down this stroboscopic evolution as some UF, which I write as e to the power minus I HFT. And what we were doing was doing these inverse frequency expansions to determine HF. Okay, so that's where we were. In this whole process, somehow I started off by telling you that, okay, this looks very much like the Bloch equation that we encounter when we deal with periodic potentials, right? So all, be a basic condensed matter 101 deals with periodic potentials. You write down things in terms of these Bloch waves and one-year functions and so on. So that is true, but I never actually exploited that analogy further. We just went on to derive HF, right? So what I'm going to do today is I'm going to put that analogy on a firmer footing, okay? And to do that, I will start off by trying to explore the properties of these states, okay? So what I'm going to do is, I'm going to say that this psi of t, right, this can be written down as sum over n Cn psi nt, okay? It's not a problem because this is just a redefinition. This is what I just call Cn psi nt. But now you note that if your initial state was psi n0, which means, or that you were initially localized in one of these C modes, if Cn was 1, then you would just evolve as psi nt, right? So these psi nt's here are actually the solutions to the Schrödinger equation. Does that make sense? Because any generic state, I'm decomposing into this basis of states. So each element of this basis is a solution to the Schrödinger equation, right? So let us then explore the property of this state further. So let me write down, just for the sake of pedagogy, being pedantic here, let me just write it down as this. And I know that phi n t plus t must be equal to phi n of t. And whenever I have such a periodic function, there is a natural thing that one likes to do, which is you take a Fourier transform, right? So you expand it in a Fourier basis. So then it would make sense to expand this as sum over n e to the power minus I m omega t phi n. Right? Sorry, what? Sorry, yeah. Yes. Okay. So now let me write down the explicit form of the Schrodinger equation here. So if I write down this I del t psi n t is h of t psi n t, this yes, these are the eigenvalues of HF. Only thing that I have said is that because psi of t is written as Cn psi n t, so these psi n t's have to be the solution of the Schrodinger equation. Because if I had set C to be one of these C's to be 1, then I would just, this would describe the exact evolution, right? Good. So what I do is, I want to just plug this in here, okay? And when I do this, what I will get is En plus I del t phi n t is equal to h of t phi n t. This step is clear. All that I have done is I have put in this form here. So the first derivative gave me this, then I put this inside. Okay, this is ht, and what I have done is taken e to the power minus I n t common on both sides and cancel it out. Right? Okay. So, so one thing that you see is that these phi n t's, right? These are the solutions, or these are the eigenstates of this operator h of t minus I, sorry? Hey, yeah, that's right. H of t minus I del t phi n t is equal to En phi n t. Okay. I just realized I had forgotten to mention this yesterday. These ENs are called quasi-energies, okay? Because you know that energies are not well-defined quantities. The energies are going to change, okay? But these are time-independent quantities. These are called quasi-energies. So often this particular operator is also called a quasi-energy operator because it will act on this and this will give you the quasi-energy, right? Okay. The quasi-energy eigenvalues are of HF. Yes, yes. So it describes basically my the stroboscopic time evolution. Yes, well. Yes, yes, absolutely, absolutely. So this is exactly, so the next step, if you remember when we do band theory, in again continuous matter, one of the ways to do it is you write down the Schrodinger equation, then you expand it in the Fourier modes of k, and then you get ek as a function of k, right? So we are going to do something similar here now by transforming this into this Fourier basis. Okay? Yes.
This satisfies this eigenvalue equation.
That's right.
And now, so So this operator must be related to the H because phi ends up the words.
Yes.
So
Very good. Yes, so that is, that is exactly what I want to do today. I want to actually tell you how this happens. For reasons of nasty algebra, there will be steps that I will just refer to, but this is exactly what we will do. This is exactly what we wish to do. Okay? Oops, sorry. Okay. So then the next step, as you can imagine, would be that what I want to do is I want to write down this. Okay, this being said, now what I want to do is let's get back here and write down the expansion, this expansion here. Okay, let us plug that in here. Okay, sensible. So if I do that, so let me just take from here. What I do that is, then what I get is En plus m omega phi n m is equal to sum over m prime h m minus m prime phi n m prime, where I have written down h of t also as sum over m e to the power minus I m omega t hm. So what I do is I take the Fourier transform of h, right, and then things are easy. I just make sure that I get the same thing on both sides. Now you can see, once I have done this, I have an equation where all the time dependence is gone. This is a completely static equation, right? So this is a nice eigenvalue equation which I can write down. So H has a structure. Let me try to give you that structure. Okay. So let this be H0. So H0 minus H bar omega, H0 minus 2H bar omega. Oh, sorry, plus. This is H0 minus H bar omega, and so on. And over here, I have terms like H minus 1, H1, H minus 1, H1, H minus 2, H2. This is okay. Let me walk you through this. This is, so what I have is I have a block diagonal structure almost. Yes. Can I always write, this is just a Fourier transform. So, yeah, yes. Okay. So, let us look at the structure. If I look at this, the diagonals, right, this block diagonal, this comprises the H zeros. Okay. This is the, basically, this does not have any of the m omega, so the diagonals, as you would see, it correspond to m being equal to m prime. Okay, so when that happens, I have an eigenvalue of En plus m omega. Okay. So this is basically if one of these had h0, the other has h0 plus h0 plus omega, the other next one is h0 plus 2 omega, and so on. Okay. These other terms here correspond to h m minus m prime. Okay. So this has terms like if I am connecting this to this, then I have to go, this is the term that connects it, and vice versa. So if you look at this structure, there is a niceness to this structure. What it is telling you is that in this space where everything is now time independent, you have several copies of the system that are each separated by an energy of h bar omega.
Just one clarification.
Yes.
These phi-ns are the expanded part of the phi-n key, right?
Phi-ns are the harmonics basically. Yes, yes. Okay. Yeah.
If these H1s and H2s were 0, it would be easy to see that, but right now, how can you?
No, all that I'm saying is that this is very good. So I'm not saying that these are disconnected. What I'm saying is that what the block diagonal components are giving you are these. What the off diagonal components are give you are actually coupling between these. Okay. There is a rather nice, appealing sort of interpretation of this, which is that I have all these components which are separated by h bar omega, which basically you can think of this system as being dressed by a certain number of photons. That you have a certain system and that also has some L number of photons, which gives you an extra energy of L h bar omega. Okay. If you have to go from one to another, you have to either gain photons or lose photons, okay, which is given by this h m minus m prime. So all these things that connect one to another, okay, these you can think of as processes that gain photons or lose photons. This is an analogy. I'm not saying that this is what is happening. After all, we are driving an isolated system. But this is one way to see what is happening here, one way to sort of pictorially see what this represents. Okay. Go ahead.
So, I just have confusion. If you take Fourier transform in the space is discretized.
Yes.
Then I can think of the discrete Fourier transform, but here time is continuous. You're asking
Oh no, I can do the discrete Fourier transform because you see, when we were even doing the lattice originally, we had taken Vx equals Vx plus a. If you remember this general Bloch's theorem's derivation, what you do is you have a Hamiltonian which is something like this. Okay, where Vx is Vx plus a, but everything is continuous. Everything is still continuous in space. Okay. Similarly, here what you have is something analogous with something in time which has a discrete time translation symmetry, even if it's continuous in time. So as long as I have a discrete time translation symmetry, I can always break it up into discrete Fourier modes. So that's why we are able to break it up into discrete Fourier modes. Yes. Yes. This is my. I should. Yeah.
H1 is the H0 plus omega, H2 is the H0 plus omega.
So no. So what the H1 and H2 are doing is these are sort of off diagonal components. H of m minus m prime. Okay. So if I read it off from here, you have En plus m omega. So these are diagonal precisely. Here you have, when m equals, you have something corresponding to m equals m prime and something corresponding to m not being equal to m prime. Okay. So then what I am getting here is when m equals m prime, these are the diagonal components. Okay. When I have h1, this is m minus m prime equals 1. Okay. So what this means, what H1 is telling you in this picture is basically you are absorbing what that element of the Hamiltonian is doing is it's enabling you to absorb one photon and go up one level higher. So basically, again, if I write this whole thing, right, what I have is this, I can write this whole equation in this form. Let's say, phi 1 or phi 2, whatever, up to phi n. Okay. So I write down this whole set of eigenvalue equations, right? And what I would then have is that for each of these, I'm going to write down the En phi m equation, right? So basically equals En So the point is that this over here corresponds, has many n's. This over here just has one m. This over here has many m's. Okay, that will contribute. So what I want to do then is to write down this whole set of equations and use it to write H equals E phi. And these from there I'm going to read off what are the eigenstates, eigenvalues, right? So here I have these things. I have the diagonal terms where m is equal to m prime. Okay, these are basically the terms which correspond to my average Hamiltonian. Okay, and then what I have is terms which are off diagonal. In this basis, there are terms which are off diagonal that couple things which lie between h0 and h0 plus omega or h0 and h0 minus omega, right? So then I can imagine that you can think about this as a process where what you have in this picture are these several infinite number of copies of the system, each of which has h0 plus a contribution that comes from having, say, L number of photons. And then you have these off-diagonal terms here that couple you from one of these to the other strands. Okay? Good?
These photons that you are absorbing as the periodic rise.
So this is, yes, so but I want you to be a little careful. This is at the level of an analogy at this moment because this is the system that I have taken, this is just an isolated system. So I have actually not coupled it to something outside from where it is absorbing a photon, right? The other thing is that if you were to truly absorb a photon, so you would have things where this process would lead to some Cn dagger acting on the number of photons, okay, which would give you a square root of n enhancement, which this does not have. Okay, so all that I'm saying is this is a way to visualize what is going on, but this does not literally describe a system coupled to an external field. Okay, so this we are still doing an isolated system, but this is one way to interpret the picture, the structure, that I have several copies of this. Okay, now I'll tell you where you have come across this structure in a more basic setting, which is again band theory. So if you remember, there is something called the reduced zone and the extended zone and the repeated zone in band theory, right? So what happens there is in this kind of extended zone kind of picture, you have the same value of the energy, which is now shifted to a different k, right? So here you have something similar, that you have the same h naughts which have been shifted to different energies, different omegas. Okay. Now this picture will be, I will return to this picture soon because this will be, well.
that epsilon n
Yes.
is the eigenvalue of the effective Hamiltonian, which is h and time derivative,
That's right.
not the h itself.
No, it's not. It is this one. Exactly. This one.
Yeah.
Yeah.
So when you Fourier transform that and apply it on phi of n, I would expect it to mix between phi n and different n prime.
So the point is that, see, here what I'm doing the Fourier transform of is this particular object. Okay. So when I'm doing the Fourier transform of this, I still have this h of t here. Okay. The goal, in fact, at some level, I'm going to show you right now. What we want to do is that we want to actually get this down to a block diagonal structure where the off diagonal elements are gone. So it is possible to do that. So that I will.
In the last equation on right hand side,
Hmm.
h n minus n prime acting upon phi of n,
Yes.
that is not necessarily will give you a state which also have an index n.
No. This is the Fourier. So what I'm doing is the following. This is my Fourier transform. So you are happy with the left. You are happy with this part. Okay. So here I don't have. I have m prime. I am summing over m prime. I have Fourier transformed h, and I am taking the Fourier transform of phi n, and I am collecting terms such that I am only left with the e to the power minus I m omega t here. Right. So once I have done that, I end up with this eigenvalue equation, which has a structure like this, which would correspond to basically having multiple copies of the system that are coupled. Okay. And these, all the, if I am able to diagonalize this, all the eigenvalues would then follow this equation essentially. Okay.
So I think this this that is written this phi 1 phi 2.
Yes.
Then I think this phi 1 1 phi 1 2 phi, I mean here.
Oh yeah. Sorry. I should. Yes. Let me just make this notation clearer. Okay. So what I want to do is.
On the nth guy.
Yeah. Yes. Sorry. Let me call this L, which is En, phi n1, phi n2, phi n L. Yes. No, that's right. So what we want are these eigenvalues En, right? So there is, of course, as you can see, that while this gives us a time independent formulation of the problem, this is now an infinite dimensional matrix. Yes, go ahead, please.
So this phi n, you lost stop at n, right? They are infinite.
It's an infinite number. Yes. So that. Yeah.
So h is actually infinite.
Yes, infinite. That is exactly the thing. So H is an infinite cross infinite dimensional matrix. So while I have a time independent formulation of the problem, I still am left with this big task of or an impossible task of diagonalizing an infinite cross infinite dimensional matrix. Right? Okay.
So if we choose h of t such that only particular HMs are non-zero, like in cosine or something, then
So even there, actually, you are bound to get a structure. So even if you take something as simple as Hm being sine omega t or something like that, this will only, it will not have the H2s, but you will still have the H1 and the H minus ones. So this kind of a, this is a more generic structure. You can get to something simpler where you retain only a smaller number of off-diagonal terms, right? But even then it's an infinite cross infinite matrix. That one cannot get rid of. Okay?
It might be a tridiagonal matrix and it is easy to deal with.
So if it's a tridiagonal matrix, yes, it is easier to deal with. Also, what I will show you in some time is, again, if it's a if we do things again at high frequency, then there is a nice analogy here where you can see that you don't have to deal with the infinite cross infinite matrix. You can truncate the matrix. And yeah. Okay. So, but one thing that must be clear from this is there has to be some redundancy here, right? Because I initially started off with a Hamiltonian, right? It was a time dependent Hamiltonian, but I started off with a finite dimensional Hamiltonian. I have made it, I have taken, I have constructed a sort of infinite cross infinite matrix, which is time independent. But even from the time dependent Hamiltonian, I could have gotten ENs if I, for instance, if I just obtain the numerically, let's say if I obtained the Floquet time evolution operator, from there I could have obtained what these ENs are, and there would have been exactly D number of ENs where D was the dimension of your matrix, right? So there has to be some redundancy in this whole thing. So it cannot have infinite number of such solutions. So the redundancy is the following. Yeah.
The right and top of it will be h of minus 3.
H of minus 3. Yes, sorry. This will be h of minus 3. This will be h of 3. Yes. Yes.
So just
Yes, yes, please. Yeah.
this H is infinite or infinite.
Yes.
And at each time I am expanding the Fourier modes, and this modes phi n of m that depends on omega.
Yes.
And there are infinite possible omegas.
No. I am in some sense, see, there is only one omega because omega is the frequency, it's 2 pi by t. I'm just expanding it as, since phi follows, since phi of t plus t is phi of t, I can always do a discrete Fourier transform of this. True, there are an infinite number of m modes, in the sense that I am writing it as some sum over m phi m e to the power minus I m omega t, right? But the omega is fixed. At the omega we do not change.
So the modes will depend on omega, right? Otherwise you don't have this omega dependence. I mean,
So the modes will this is the only omega that I have, right? So this is how I, so of course whatever, okay, so I guess what you are saying is that this phi m, what the value of phi m is, that will depend on omega. Yes, of course it has to, right? So what the value of phi m is, that it has to depend on omega. But let's say that I have given you a Hamiltonian. I have given you a Hamiltonian with a particular period. Then my phi m's are fixed. That won't change anymore. Once I have fixed my Hamiltonian, once I have fixed my omega, my phi m's are fixed. Right? That's why otherwise, I mean, you could carry an omega dependence around, but that has to come because anyway, this I'm expanding like this, right? So
actually this is a confusion. So I was asking that whether this omega is related to capital T by 2 pi by capital T, or it's just a Fourier.
no, the omega is 2 pi by capital T. This has to be, right, because this is the Fourier transform, the discrete Fourier transform, right? This is the whole point, that if I have a discrete time translation symmetry, I can break it up into discrete modes, right? So these are the same things. Yes.
Reciprocal vector in
Absolutely, exactly. Yes. Okay. So then what is my redundancy? So the redundancy is the following. See, I had written down Sayan of t as e to the power minus I e n t sum over m e to the power minus I m omega t phi m let me just call it phi m n, right? Now I can easily do the following. I can write this as e to the power minus I e n t sum over m e to the power minus m prime omega t e to the power minus I m prime omega t phi n m. Okay, there's nothing special here. I can bring these two together and get e to the power minus I e n plus m prime omega t sum over m e to the power minus I m omega t e to the power plus I m prime omega t phi of m. Okay, so this is just manipulation, and I can label this as some phi tilde m, right? This is a common thing that has come in here. This is just a phase. I can label this as some new phi tilde, right? And so what I get is sum over m e to the power minus I m omega t. So En and En plus m omega, right? These describe the same state, right? These quasi energies describe the same state. I can always shift my En by m omega and it still get the same quasi energy. This of course is not a surprise really, right? Because how did we get the quasi energies? We got it by first writing u of t as e to the power minus I hft, right? So then what I do is then I take the log, right? So hf is equal to I by t log of u of t. So two interpretations come out naturally. One is that the log has an infinite number of branches, right? So each branch is equivalent. So these are only defined, all the energies are only defined modulo 2 pi, modulo omega, right? Alternate way of thinking about it is, if I had written down this u of t, this whole thing here would give me, instead of, if I were to write down the eigenvalues of u of t, I would get the eigenvalues to be of a form e to the power I theta or e to the power minus I theta, right? And thetas are also defined modulo 2 pi, right? So this means that all my energies are defined modulo m omega or modulo omega. So I can always, if I solve this equation and I get an energy, I can always bring it down to lie between 0 to omega or minus omega by 2 to plus omega by 2. Okay. This is the Floquet-Brillouin zone, right? So just like we have the standard Brillouin zone in condensed matter where you can bring everything down to the reduced zone, here also we can bring everything down to the reduced zone. Any energy, given a quasi energy value, I can always bring it down to a reduced zone. Okay. And
or omega.
Huh.
You also have the effect at the Floquet modes as well, right? Because they are always.
so the Floquet modes, exactly. So the fact that the Floquet modes have this independence allows me to write this, right? So this is again, if you are looking for sort of analogies to the block thing, right? So if you have ever done this block to 1 year conversion, you have this phase phase choice that you can attach to each block function, and thereby you can create these localized 1 year functions. So it's something similar. So here you have this sort of phase choice that you can add, nothing changes, but you can always bring the energies down to 1 Brillouin zone.
Once you fix the quasi energies, the functions are fixed.
Once I fix my quasi, okay. So what we will be So what we will do is that if I fixed my zone, then of course I know that what is the zone that I'm expanding in, and in that case the functions are fixed. Of course, if I were to do it, say I was doing it between minus omega by 2 to omega by 2, and you say that no, I prefer it to be between omega by 2 to 3 omega by 2, right? So then there will be a shifted thing, but yeah, basically once I have decided what is my zone of energies, after that everything gets fixed. Okay?
So basically what we're saying is that big Hamiltonian that we got,
Yes.
we can block diagonalize it.
Yes, exactly.
How will the blocks be like this H0? How big?
H0 has to have the same dimension as your original Hamiltonian. Okay, so and what the blocks will be is essentially the following: HF, the original HF plus omega, HF minus omega, HF plus 2 omega, HF minus 2 omega, and so on. And as you can imagine that just like we were doing kind of these perturbation theories like Magnus expansion, this kind of inverse frequency expansion, earlier we were doing it from the structure of U of t. We were writing down the Dyson series, and from there we were extracting what HF should be. You can actually use this structure to also get what HF should be. So if your omega is very large, then you can also use a perturbative approach to get things from there. Here. Okay? Yes? Yeah, please.
What is the quasi energy and what is this periodicity that you're talking about?
So the quasi energies are basically the eigenvalues of HF. Okay, these are defined. These are unique modulo omega, because if I add HF plus omega here, then this gives me e to the power minus I 2 pi, which is identity, right? So this structure also comes out once I've written it down in this Fourier space. I also get a similar kind of structure. So if I were to solve for the entire, suppose I had the skill to solve for the entire spectrum, what I would end up with this is that I would have a certain energy spectrum between minus omega by 2 to omega by 2, and then it would repeat. Okay? So that is something that here one of the things is that so once I fix my zone that it will lie between minus omega by 2 to omega by 2, let's say, then everything gets fixed. Okay. There is also another thing that comes out of this, which is actually maybe I'll make this analogy to Bloch's theory first. So have you heard of something called Umklapp scattering? Okay. So if you have not heard of Umklapp scattering, let me tell you, it's actually quite interesting. So if you, so we know that normal scattering processes conserve momentum, right? Now suppose you have a lattice where you have broken the continuous symmetry into a discrete symmetry. Okay. Momentum gets conserved only modulo 2 pi g, where g is the reciprocal lattice vector. Okay. So this is the notion of Umklapp scattering, that if I have scattering in a lattice where I have a discrete space translation symmetry, your momentum is conserved modulo 2 pi g. You have something similar here. If I am looking at scattering processes, energy is only conserved modulo 2 pi, modulo h bar omega, essentially. Okay, you can see it from this structure directly because this is a time independent structure. So from here I could write down a Fermi's golden rule to tell you how scattering would be. And you now know that because you have this infinite number of copies, you could scatter into different versions of these copies and only conserve energy modulo 2 pi by omega. Sorry, modulo h bar omega, right? So one of the consequences of this structure is that in standard scattering processes, instead of energy, energy is conserved is a standard thing, but here the quasi energies are only conserved modulo h bar omega. Okay. So let me actually give you sort of a proof of that. Okay. That why would this happen? This has some drastic consequences though, that I'll give a proof of this. This has some drastic consequences. The major thing is that if we have, let's say, so you have done this eigenstate thermalization hypothesis and chaos last week, right? So if you ask this question that I start off with some initial state and how do I spread, right? So you spread through processes which sort of keep your energy conserved. Okay, so which is why if you look at things at the end, your microcanonical average must equal your long time average. Okay, so you sort of go through all microstates which keep you at the same energy. Now you see that energy is only conserved modulo h bar omega, which means that this allows you to go through different processes where you can sort of go through a lot more, you can sample a lot more states. Okay, so as long as these and this becomes particularly a big thing in many body systems because you have a very dense set of states, so you can really sample a lot of states through this scattering processes. Okay, and in doing this, what's going to happen is that your system is going to scatter all over. Okay, and it's going to go to all possible states, and the eventual thing that we'll end up with is what's called an infinite temperature state. Okay, so if you are going to drive the system's energy is going to continue to increase and its entropy is going to continue to increase till it can't increase any longer. So that's what's called a Floquet heat death. So what I'm going to do is today, right now what I'm going to do is I'm going to give you sort of an explanation of why the Fermi's golden rule works, okay, and give you some justification for it. And then tomorrow we'll see how this sort of leads to Floquet thermalization or this infinite temperature thermalization. Okay. Yes.
So Floquet heat death means the initial state is actually spreading to the all block diagonals Hamiltonian.
So actually what it means is that the initial state will sort of spread over all eigenstates of the original U. Okay, so what is going to happen is that even if your initial state was a product state, you are always going to end up with the maximally entangled state at the end, I mean at long times, and all memory of your initial conditions would be gone. So if I look at one subsystem, okay, that will be described by an ensemble which is a diagonal ensemble, which is the infinite temperature ensemble.
Okay, so in this block diagonal structure, can be the whole dynamics can be only only single block, or it's actually.
So what you will get from this is that if you do everything with this block diagonal structure, because that block diagonal structure is time independent, okay, you can write down a Fermi's golden rule here which conserves energy only, okay, and write down scattering processes that conserve energy. You are going to naturally get processes which take you into other blocks. Okay, so in this structure, then you are conserving energy, but because of this all these infinite blocks being present, you naturally are able to go into other blocks. Okay, when I fold it back to keeping only one block, then this in turn tells you that your energy is, or quasi energies are conserved only modulo h bar omega. Okay, okay, is this clear? Yes, yes, please go ahead.
Suppose you start with some initial state.
Yes.
The nail, for example.
Yes.
it has a misspectrum property. So
Yes.
for a quench problem, it has overlap with certain number of states.
That's right.
And let it evolve in the quench state.
Huh.
Versus if I do it stroboscopic, like drive the system,
Huh.
then the snail state has now, I mean, one can think of that it has overlap with much large number of states.
That's right.
There are folding effects,
That's right. That's
as
right.
you mentioned.
That's right.
So is the floating ETH is a more robust statement as compared to the static problem? I mean,
Uh, Okay, so one thing is that, I think as with ETH, so one of the maybe a slightly more skeptical view of ETH is that I want to understand how statistical mechanics emerges from quantum mechanics. So I put in a structure which will give me that. So, if you look at the Shrednicki PRE, it's almost written like that. Okay, so here the idea is also something very similar, that I am, let's say that I know that if I were to drive a classical system, okay, let's take a classical spin chain, okay, and not connected to a bath, but the spins are classical, and I drive it, okay. What's going to happen is that you can do this very easily, that you will show that you will eventually sample all of your phase space, and these are all well defined quantities now, Sx, Sy, Sz we can write down, right. So you know that this is, so if you do this classically, you know that you are pumping in energy, you are driving it, and so it will explore all of phase space, and it will do it without any restrictions on what it can do, okay. So the Floquet ETH is also sort of constructed such that the quantum version will match up with this classical StatMech expectation. So in that sense, it is, I think it is very similar to ETH, but the thing is that when you have done ETH last week, you have done this, you have looked at the properties of HF, right? Or you have looked at the properties of certain Hamiltonian and said that, okay, this is going to be some kind of it will be in some Gaussian ensembles and so on. What we will show is actually this, if you generically drive a non-interacting system, you generally drive a non-integrable system, this u of t, if you look at the phases of this u of t, they don't actually belong to these Gaussian ensembles, they belong to something called circular ensembles. So the circular, and if you belong to the circular ensemble, then heating up to the infinite temperature state is inevitable. So this is all an advertisement for tomorrow's class. Okay. Okay. So I hope that the Fermi golden rule is believable. I'm going to give a proof. There is a particular proof that I like, so I'm going to give that proof. But I hope that from this structure it is believable that the energy is going to be conserved modulo h bar. Right? Okay. So yes.
So what you are addressing, like suppose I confine myself to a given block and
Yes.
I want to make a transition from one state to another within that block.
Yes.
I want to know what is the rate at which such a transition takes place due to other blocks.
Yes, yes. So the presence of the other blocks will give you certain channels which would not have come from being in one block alone. Yes, that's the point. Yes.
So do you need to make some assumptions like the ones that underlie the Fermi golden rule, that the energy levels are discrete, etc., continuum, etc.? Do you need such things?
So, okay, so what I am going to do is right now with the only thing that I assume is that my Hamiltonian is a finite dimensional Hamiltonian. So, other than that, things are going to be fairly general. So, actually, there are quite a few proofs, but the one that I'm going to use, I think, is a simple but sufficiently general proof. Yeah. So the point is that we would want to look at, so there are two things. One is that this kind of a structure tells you that if your omega is very large, then, and your h1, h minus 1s, if these are small, then you can imagine doing a perturbation theory to get an effective H naught, right? So in fact that is done, and there's an expansion called the Van Vleck expansion. So that one can use to get an effective Hamiltonian. That has this advantage that one of the things that we were seeing yesterday was in the Magnus you might have to go to the rotated frame and so on. Actually the Van Vleck that way is very robust, because as long as your H1 and H minus 1s are small compared to your omega, you can always do this perturbation theory, and it will naturally, the perturbation theory is built such that it will naturally take you into a rotated frame. Okay, so that maybe I'll give a reference to that. So one is that way you can design an effective Hamiltonian, and that is one of the main things that motivated a lot of the study in Floquet, was that we wanted to design effective Hamiltonians that were not present in its bare form. So I have some system that has certain properties, but I can't do much more. I put in a certain kind of drive, and if I'm able to tailor my drive properly, I will be able to realize Hamiltonians with a better, more desired structure which has certain interesting properties, right? So all of this builds towards getting such HFs. Now the question, but one thing that comes out of doing this, that in building towards this kind of effective Hamiltonian, is that you now know that your scattering here is much more, your number of scattering channels have opened up much more. So you also have to account for the stability of this system. So it's one thing to talk about, oh, I want to go to a effective Hamiltonian which has an interesting ground state, which I wanted to realize, and that was what mostly people were doing back in the day. But now we have to see that here there is no notion of a ground state, because for every ground state in one block, I have a block below that, and I have a block below that, and so on, right? So the stability of these states now become questionable. So of course I can have eigenstates, there is no question, there is no problem, I can have eigenstates, but even the ground state of HF, this can become unstable because of these kind of scattering processes that are available, that can happen. So now I have to then build up a formalism to calculate or compute at what rate do these scatterings happen, and once I have that, then the goal would be that what can I do to reduce this scattering, what can I do to stabilize the state, right? So what I want to do is to build up the formalism to tell you why scattering happens and why generically heat death is inevitable, we can't help it. But then the final class, which will be tomorrow afternoon, I will talk about something called pre-thermalization, where we will show that if you drive it with high frequencies, if you drive a Floquet system with high frequencies, then you would be able to stabilize a state for exponentially long times. And this is nice because it ties up very well, because after all these HFs that we were trying to derive were all done through an inverse frequency expansion. They work really well at high frequencies, and also at high frequencies if we drive we can stabilize the system. So this sort of gives us hope with Floquet that Floquet works, and at least we'll be able to create states of phases of matter or states which would be stable up to very long times, certainly for the time scales of experiments. Yes?
You said like using Floquet you can stabilize a state, but like without heating up the system?
So the heating up is, so the point is that the heating up is almost inevitable. There are certain ways that one can avoid it. For instance, if you have an integrable system, or you have there are certain ways in which you can avoid it, but those are often fine-tuned. Generic thing is that I drive an interacting system. If I wait long enough, it will go to the infinite temperature state, right? But the question is that how long is long enough? Can I control that long, right? And what I'm going to show is that driving at high frequencies, by making the frequency high, I can control that long, and so I can stabilize it for stabilized Floquet phases for very long times. Okay. So yeah. So but first maybe what we'll do is we will just build up this Fermi's golden rule to connect to Floquet ETH, which will be tomorrow, and then tomorrow afternoon we'll talk about this high frequency pre-thermalization. Yes.
So for ETH, even in non-integrable systems, if there is some Hilbert space fragmentation or
Yes.
varying disorder or something,
Yes.
you can not follow.
That's right. That's right. So, so there are two things. One is here also we will maybe talk about it a little more. So if you put in strong disorder into a system, then the system can, in principle, host a many-body localized phase, which is an eigenstate phase. The stability of this phase has been questioned in recent years, so we should be a little careful. Now, on this many-body localized phase, if you drive it weakly, many-body localization can persist and the Floquet ETH can be violated. Things like fragmentation typically in Floquet systems occur pre-thermally. That you can get Hilbert space fragmentation, which will last up to a long time, but eventually it will thermalize. So, evading thermalization altogether in Floquet systems is difficult. So there are certain, there are certain fine-tuned ways in which you can do it, but the only sort of robust way was purported to be this many-body localization, but that is sort of under question. Okay, so let me tell you then how this works. So what I'm going to do is I'm going to say that whenever we do these kind of inverse frequency expansions of any kind, we get an approximate Floquet Hamiltonian. Okay. So let my exact Floquet Hamiltonian be the approximate Floquet Hamiltonian obtained through inverse frequency expansions plus some additional term V. Okay. So what we want to see is we want to see the effect that this has if I start off from an eigenstate of HF. Okay. So let's say my initial state psi t equals 0 is an eigenstate of HF. Okay. So what I want to do then is I want to calculate in some sense this quantity. I want to calculate, what would be so I want to do something like this. I want to calculate what is the psi t equals 0 overlap with psi t, okay, at long times. Now, so V is the additional. So this is the exact HF. This is approximate HF obtained from Magnus or whatever is your favorite inverse frequency expansion. Okay. This is the small part that, of course, whenever you are doing a Magnus or something, you stop at some order in the inverse frequency and you say, well, my frequency is large enough, those things probably does not matter, right? So that is that additional part.
So this V is of the order 1 by omega.
So depends on where you stop your HF. So generally there is an optimal order to stop HF. So it depends on where you stop. It can be. So we are going to treat it perturbatively. Let this be a small thing. Okay. Okay. So actually, so this is the thing. Actually, let me even start off, maybe not even with this. Let's do the following. Hold on. Let us write the following. This is a thing that assumption So what we are going to say is that we are going to assume that the state is going to evolve in such a way that at any point my state is described by some density matrix which is Pnt Nn, where n essentially Hfn is Enn. Typically we want to start off at a point where one of this is 1, right? And then we want to see how this evolves, right? So for this what we can do is we can write down a master equation, right? This is a standard kind of thing that one does. So the master equation is telling me that there is a rate at which I am going from other states m to the state n, right? That will contribute positively, right? So this is Wm to n Pm, and the other one is minus Wn to m going in the reverse direction Pn, right? Yes. This sum over n Pn. This is rho t. This is the density matrix. Rho t. So my assumption is that at any point I'm saying that at least we can say that at every point I'm writing down the density matrix that describes the system as the probability of being in a state n, which changes with t. And then what we are doing is we are writing down just this master equation that is characterizing how one goes from.
Assuming that V is very small.
Small, yes.
So if I look at the eigenstate properties of HF tilde, then those properties will be mapped to the infinite temperature ensemble if I wait long.
So this HF tilde will actually not give you the infinite temperature ensemble, because you see this HF tilde is, after all, it is a static Hamiltonian. Okay, so if I look at HF tilde generally, this will actually correspond to one of your Gaussian ensembles. Okay, so yeah, so if on the other hand, if I am looking at the exact, and since it would correspond to a Gaussian ensemble, what would happen is that within this HF tilde, if I were to calculate energy absorption or something after some initial evolution, once it has reached sort of all the once it is spread over all the states corresponding to HF tilde, it would have stayed there. Now the claim is that what I'm saying is that suppose I have started off even at one of the eigenstates of HF tilde, then this additional part will still cause me to go between different states. So actually, when we will do this tomorrow, when we will try to characterize the level statistics, the level spacing here, what we do it is from these essentially from these e to the power I thetas, which are my eigenphases, those have a slightly, those actually belong to this circular orthogonal ensemble. So if you calculate this ratio R, which is what we often do to characterize these things, so this R is slightly different between the Gaussian and the circular values. So if you do very good precision numerics, you will actually be able to distinguish this. So yeah, so I will actually tell you tomorrow how this works, okay? But this alone does not tell me that I'm going to go into the infinite temperature. All that I'm saying is that even from this, I'll tell you that even if we had started off here, this V would still cause these kind of transitions to places which are on, as long as the energy is conserved modulo h bar omega. Okay, so this is so I mean, I guess the point where this was interesting was that initially, as with Fermi's golden rule in general, you need a perturbation. So the initial formulations of Fermi's golden rule was done with treating things like H1, H2s to be small quantities. Okay. This formulation tells that Fermi's golden rule can be done for anything. Okay. So as long as I have a HF and then there is a small part that is away from it. Okay. So, so even if you have a system which is very strongly driven, if you have a way to get an approximate HF, okay, and you have some additional part left, then even then you can do Fermi's golden rule by this manner. Okay. So this is the standard sort of rate equation that we do in any time-dependent perturbation theory. Okay. So what we will show before we will show the following. We have 10 minutes, so hopefully that will work. So let me tell you what I have written down here. The actual UF, the actual U that corresponds to the exact time evolution is different from whatever would correspond to e to the power minus I h tilde f, right? So let me call the actual sorry, no problem. So I want to just tell you what are the different terms here. So for doing that, what I'm saying is that my actual Floquet operator is U, which is e to the power minus I hf, how have I written this, hf exact t, right? I also have an approximate operator under which there would be no evolution here. That approximate operator is e to the power minus I h tilde f t. Okay. I can define a delta UF as UF dagger U, which is not equal to identity. Okay. So this delta UF causes transitions and the formula for that is the following. This rate at which you are going to go from Wm to n, one is the rate itself dictates that there will be a omega kind of thing, right? Then you have this delta function which is telling you energy is conserved modulo h bar omega. I have written it in terms of thetas because the thetas are essentially saying that it's this uf n is e to the power minus I theta n n, okay, and then I have this part here which causes the transition, okay. So I have written everything in terms of delta u, not as a small perturbation to the Hamiltonian. If v was small, I mean, in certain cases one can write this as a small perturbation, but I've generally written it as delta u, okay. This is fine, okay. So this is what we will sort of prove here.
Sorry, why is it proportional to omega?
So of course I will prove it to you, but this is also dictated by the fact that this is a rate, so dimensionality, okay. Okay.
My states were eigenset of this
UF. Okay. So the first thing that I want to do is I want to expand the original u linearly in terms of this delta u. So for that what I want to do is I want to write u as uf dagger u, which is uf delta u, which I am going to expand as uf times identity plus I delta k. Okay. This is an first order expansion of delta u. Okay. What is p m going to n? This is essentially n u to the power n m mod square. This I can approximate it as k equals 1 to n uf to the power k delta k. Wrong choice, maybe I'll just write it as a equals 1 to n uf to the power a delta k uf to the power n minus a square. Okay. I know it's getting late, but hopefully you are still with me more or less. So this is uf identity plus I delta k. I have just substituted it in here, kept terms which are linear in delta k, right? So this is what I have. This is a sum here. Okay. So this sum I know how to write.
That is u to the power small n, first PMN equals to small n or capital N?
Which one? This one?
Yes, no. After equality sign, that u to the power n.
This is u. Oh, okay. So maybe, yeah. I should be careful with this. This is capital. Yeah. U to the power n, m. Yeah. So this I'm splitting up into all of these, and then I'm taking this out. So what I would end up getting is a bunch of these e to the power minus I theta n minus theta m k's. K is the lowest order contribution. So this is the way in which Fermi's golden rule is coming in, because we are keeping the lowest order contribution. Okay. So after this, So what have I done is nothing very special. What I have done is from here I have this is not K, it's A in this language. So I have just acted these on this on this, okay, and this delta K UF to the power n, basically that comes out as this delta U M n square.
This is your W, by the way.
This is
M to N, right?
so the W so actually the way that I'm going to define the W is basically this. That is the P M2N by NT. Yeah. That is, yes. That's almost W. Yeah. Okay. So now as with any treatment of the Fermi's golden rule, we are going to take the limit of long times, right? Which in this case becomes a limit of large n. Now I'm going to appeal to something that you have probably learned at a certain point, that a sum over this kind of e to the power I thetas can be written as a delta function, as a sum over delta functions, right? So I'm going to do a little bit of an approximation. So the first, there are two parts to this. One of these I'm going to write as a delta function, and the other is something that I'm going to use to keep track of n, okay? Because if one of these is the delta function, this is at large n, but n, if n is not exactly equal to infinity, whenever theta n is equal to theta m, this would give me 1. So I'm going to use one of these to count n and the other to keep the delta function. It's a slight bit of approximation, but physicists are allowed these things, okay? So this is going to give me 2 pi n delta, just this part here is going to give me this 2 pi n delta theta n minus theta m minus 2 pi l, and then this part still stays. So I have n delta u m mod square, okay? And then if I am interested in w m to n, which I define as p m to the n by nt, this becomes, I just want to divide this by nt, and this will just give me omega n delta u m square z delta theta n minus theta m minus 2 pi l. Mod square where? Yes, this is the part where I said that I'm doing a approximation, because I'm going to use one of them to give me the delta function, and because n is large but not infinite, I'm going to use the other to count how many of these are there. So every time theta n is equal to theta m, which is when the delta function will have a weight, this will give me a value of 1. So if I write it as this times the conjugate of this, one of these I'm using to get the delta function, the other to count n. Okay, I am ultimately interested in the limit of n going to infinity. So this is a reasonable approximation. And so the net result of all of this at the end of the day is that I have this rate of going from one eigenstate of HF to another happens with energy conservation modulo h bar omega, or modulo omega. So this in turn tells us that any Floquet system has many, many more ways to spread through state space, and no matter how strongly driven, weakly driven, whatever your system is, this will always eventually spread. Okay, so the consequences of this thing and is something that we are going to look at tomorrow. So, I mean, of course, we have preempted it. This is going to lead to a Floquet heat death. But how does this come about, and what exactly is then the Floquet version of ETH? This we will do tomorrow. Okay. Thank you.
So, any questions?
So
Yes.
just technical.
Yes, yes, please.
How did that delta K become delta V?
This one, right? So here what we are doing is the following, that I have, so when I'm calculating, when I'm sort of counting this thing here, right, there I have a UF to the power n minus a here, and I have this UF to the power a here. So what I'm doing is that I'm retaining one of these UFs, okay, such that I have UF times I delta k inside, and the remaining I'm taking it out as because it's a mod square, I'm taking it out as a overall factor. So that's why I am able to. Yeah. So okay, let's just put it like this, that what is my delta U? My delta U is UF times sorry. So delta U is basically UF times I delta K, right? So when I am acting on this thing here, when I am acting on n UF delta K m mod square, right? N is an eigenstate of UF, so you can take it out. Yeah. So you might as well have written it as delta K, but it's the same thing. Yeah.
If not, any question?